Hi, Calc BC. Welcome back. Today we're talking about arc length and surface area. So arc length we did a little bit last year. It was kind of during the shutdown time, so I'm not sure exactly how much you're going to remember. So we will go through the formula for it and then a quick example of how to find arc length. And then surface area will just be, when we take that arc then and rotate it around an axis of revolution, um, how do you find the area of that surface? So that's our plan. Let's just jump over here to our whiteboard today, and let's talk about our arc length first. And I think you'll remember the formula for arc length. Um, maybe it's an integral, right? The length of the arc s is usually the variable we give it, but you can call it whatever you want. Um, it's the integral along the interval a to b of the square root of 1 plus f prime of x squared dx. And so, when you have your arc, whatever it is, you look at the derivative, you square it, you add one, you put it in a radical, and you integrate it from a to b. And that gives you the length of that arc. And so what I'm going to look at here is an example, and we'll show how this function works. And since we're back in chapter 6, kind of before we finished up all of our integration techniques, these are going to be the ones that are sort of those magical functions. There's a lot of algebra involved, but you'll see what happens in the end. So the idea, of course, is just, in general, if I have my, if I have my axes here, and if I have my function, here's my function, let's say, and I want to know how long is the arc along that curve going from, maybe this point here over to this point here. This is A and this is B. Then that's what this integral will find. So, oops, trying to match up my original drawing there. You get the idea, I think. Just that green section of the graph. All right, I'll quit my playing around with my drawing skills that are so obviously lacking on this tablet. And let's take a look at an actual function. So in this case, the equation that they give us is one of these magic ones. So it's x cubed over 6 plus 1 over 2x. And they want us to find the arc on the interval, looks like 1/2 to 2. So, and so I'm going to start off by just taking the inside of that function and say, well, okay, because I know I need to find the derivative. So let's find dy dx. Well, obviously, if I bring down the power, right, the 3 and times by the 1/6, I get a half. So this just turns out to be x squared over 2. And here, the x is to the -1. So when I bring down the -1, I actually get a -1 over 2x squared. There we go. There's dy dx. Now, looking back at the integration formula there, I see that I actually need dy dx squared. Well, when I square this binomial out, right, the first term is, x to the 4th over 4 minus, now when you multiply these two together, right, the x squareds will cancel, but we're going to get a -1/2. I'm sorry, -1/4. And then you double that, right? You double for the middle term. So you get a -1/2 right here. Okay, and then the end term, right, we get 1 over 4x to the 4th. Okay, so yeah, if you didn't follow that or that was too fast, just look up a minus b quantity squared. You get a squared minus 2ab plus b squared. Oh, shoot. Well, there's a squared over there. Yep, there we go. All right, then remember inside the radical sign, it's 1 plus dy dx squared. Well, what happens if I add 1 to this whole thing? right? The 1 and the -1/2 combine. So I get 1 plus dy dx squared is actually x to the 4th over 4 plus 1/2 plus 1 over 4x to the 4th. And if you're thinking, well, what did I really do there? Guys, that's a perfect square binomial. That's x squared over 2 plus 1 over 2x squared quantity squared, right? And now you kind of see where we're headed with this. Because then, of course, inside the radical, that's what's in there. So when you square root it, because remember, the integrand is actually the square root of 1 plus dy dx, or f prime of x, I think I wrote that squared. Well, that's the square root of x squared over 2 plus 1 over 2x squared squared. They cancel each other out. So in the end, my integral is x squared over 2 plus 1 over 2x squared dx. Now, I know we've got limits, but before we do that, let's just figure out what this integration is going to do. Oh, well, look, I'm going to add 1 to the power and divide by the power. Now, this is 1/2 x to the -2, so I'm going to add 1 to the power, give me -1, right? Does that look really familiar? Look, all we did, that whole mess of algebra, all it does is change the middle term from positive to negative. So anyway, that's just the kind of magic functions I was talking about. But the good news is, remember, this was on an interval from 1/2 to 2. So our arc length then is this evaluated from 1/2 to 2. So we'll put that in there, and this is the 8/6 minus 1/4, minus put in a half. Anyway, you get the idea. I'll spare you the arithmetic here, and get that arc length would be 33/16. Okay, so there's arc length. I think what you'll find is a lot of the functions that we are in this section, because it's early on in the book before we had all those integration techniques, is they all work out pretty smoothly. The algebra is designed so that you don't have a square root left hanging in there. For the most part, I think you'll find that those are pretty straightforward. All right, so that's arc length. What about surface area? Well, as we start to think about surface area, what I want you to think about, surface area, okay, is let's start with just a straight line. Okay, so if I had just a straight line that I rotated around an axis, okay, yeah, it would make a ring kind of thing, right? All right, and what I'm saying is I want to find just the area of the surface of this ring. Okay, so imagine if this was a strip of paper that we had just put into a ring. How would you find the area of just the paper that's making up this ring? Well, if you're thinking, all right, well, I know that I can find this radius, right? Now, if I just took a pair of scissors, just cut that ring and laid it out flat, what would it look like? Big old rectangle, wouldn't it? And the length of the rectangle, right, is actually the circumference of the circle, right? That's this whole thing right here. That's the circumference, which is just pi times diameter. And then the width of the rectangle, that's just this distance here. So the area, the surface area of this one little rectangle rotated around an axis is just pi times diameter times the width. Obviously, if this is a radius, then we will probably substitute in there 2 pi r times our width. And that's how we're going to find the surface area. Now, the tricky bit here is we're not always dealing with straight lines, right? So how do we find that width of what we're revolving around? If I had a more complicated shape, say some kind of curve, and I wanted to find the surface area that gets created when we revolve this around the x-axis. Well, if we break it down into small little pieces, if I just revolve that little red region around the x-axis, oops, let me fix that location there. I sort of have the same idea, just on a vertical scale here, of what I just did, right? I still need the diameter or the radius, right? But the width of that little band, that's an arc length. So when we do this with a general or a generic function, okay, well, look, the radius you can see is f of x here. And we have that arc length there. So when we go to revolve this around an axis, then the surface area, big S, capital S, is equal to, well, the integral from a to b, right, of 2 pi times the radius. Okay, in this case, that's the function of x, right? Times the length of that arc, which we know, 1 plus f prime of x, quantity squared. There should probably be a dx on there. Sorry, got to squeeze that in there. Now, the reason that r of x and I have f prime of x written in there separately is they're the same right now the way I've drawn this picture, but that's because I'm revolving around the x-axis, okay? Axis of revolution right here, easy peasy. R of x is equal to f prime of x. But if I'm revolving around a different axis, okay, then r of x will be different than f of x. And so when you revolve around like the line, y equals 2 or something like that, well, then the radius function is, right, top function minus bottom function, 2 minus f of x. Okay, but the arc length is still done using f prime of x. So that's why there's a difference in there between the two functions. So yeah, when we take a function like, let's see, our first example here is just using the very simple function f of x equals x cubed. And it's going to be revolved around the x-axis on the interval 0 to 1 around, it's supposed to be a u, not a w, around the x-axis. Okay, so let me just sketch it out because drawing a picture is always a good idea. Okay, so here's x cubed. Let me get a different color here. Going like this on 0 to 1, so that when we revolve around the x-axis, right, we get that sort of, like horn bell kind of look. Okay, but now it's not the volume of the solid of revolution, it's just the area of that sort of weird pyramid-ish shape. And so my surface area will be the integral, well, the 2 pi could come out, right? Yeah. That makes sense. So my radius function is equal to f of x in this case because I'm revolving around the x-axis. So x cubed square root 1 plus the derivative of that is 3x squared dx. Okay, and so now we can find the surface area by just evaluating this integral. If I change the axis of revolution, and that's why I want it, you can probably see how to do that integral without too much help from me. Because now it's a u substitution. You can sub out the stuff inside the radical, right? Because you're going to get 1 plus 9x to the fourth. The derivative of 1 plus 9x to the fourth, right, is 36x cubed. You've got the x cubed in there. You just need the 36. So, okay. So I don't want to waste a lot of time doing the integral because I know you can do that. I want to say, take the same problem. So this is part A. Part B says now revolve around y equals 1. So that changes the picture. Okay. So, let's get my axes turned back into black here. Okay, so if I take that same picture, come on, like so, but now I'm revolving around the axis, y equals 1, that's up here. Okay, that means that my little tiny slice of arc down here is going to get revolved up, right? It's going to go this way. So my arc length will still be square root of 1 plus 3x squared quantity squared. Okay, what's different is my radius function now, right? Oops. I have to come down here and say, oh, okay, so the radius right here is 1 minus x cubed, because it's always top function minus bottom function. So my arc length will be 2 pi integral 0 to 1. That hasn't changed. Now my radius changes, 1 minus x cubed square root of 1 plus 9x to the fourth dx. And so now you have to deal with how am I going to do that integral. Okay. And again, I'm not going to go through the integration with you. That one would be a little bit tougher. I mean, on the one hand, you're going to have the same integral as you have above, but you are going to have to distribute that the radical 1 plus 9x to the fourth. And so you are going to have to integrate 1 plus 9x to the fourth square root. And there's lots of techniques that you could look to for that. So let you ponder that and see how you would go about doing that. So anyway, that's how we do surface area. It's again just kind of leveraging that arc length formula from here and just taking that arc and then rotating it around an axis. All of the ones in this section I think are set up so that they're pretty straightforward. More like part A of this one, not like part B of this one. Part B would be definitely a higher level problem, something you would see later on in the textbook. So, all right, guys, that's it for today. Hopefully that makes some sense. Go ahead and give these ones a try if you want ahead of time. If you're like, oh, I'm okay, maybe you could just work out the example problems here. I just tell you that this top one here is example 6. This is example 6 on page 446. So if you want to give that one a try, you can kind of see how they did it. This one is my own example. This is one that Mr. Ray made up. So there's no solution for you to check out in the book. You'll have to give that one a try on your own, and then we can talk about it in class if you want. But all right, thanks, guys. I will see you in class.